So today, I will talk again about scanning tunneling microscopy and about AFM, the same as last time, but with more details and a bit more formulas. We will discuss two modes of STM, constant current mode and constant height mode. I will try to explain you a bit more with a bit more details what about PID controllers and how they work in the feedback loop control. And we will start talking about major AFM imaging modes: contact mode, semi-contact mode, and non-contact modes. We will talk about them in more details next lecture, but today it will be only introduction. And and force distance curves, why we need them, how we can calculate them, and so on. So the difference between STM and AFM. So on the left-hand side, you can see STM. On the right-hand side is AFM. So again, just a reminder, so in STM, voltage is applied between a metallic probe and the sample. So the voltage is typically less than 3 volts. And then when the probe is close enough to the surface, it's about 2 to 4 angstroms, the voltage will result in a current due to tunneling effect that we discussed with you yesterday, on Monday. And when the probe is far away from the surface, then the current will be 0. So for STM, which is very important, that the probe is very, very sharp. And the main component of it is usually composed from tungsten, and it is connected to a piezo electrode containing sometimes it's 3 perpendicular piezoelectric transducers, sometimes it's just a cylindric one, and then the tip will be brought within, how I've already said, 2 to 4 angstroms up to nanometer, and we will be able to image electrically conducting samples. So at the close distances, the electron clouds of the metal tip will overlap with the electron clouds of the surface atoms, and then the tunneling current will be generated. So the magnitude of this tunneling current is dependent on the bias of voltage applied and the distance between the tip and the surface. Regarding AFM will operate on a very different principle. So the key component is the cantilever that has a tip on it. This tip will, in most of the cases, touch the surface. We will discuss non-contact mode as well, but by default, the tip is touching the surface. And the force is very small, about piconewtons, and will be detected by AFM. So the AFM measures the deflection of the cantilever caused by van der Waals forces. And because if we compare STM and AFM, because of the exponential relation of the tunneling current and distance, STM has a bit better resolution than AFM. And then at STM image, we actually can see an individual atom, while in AFM, we still can do this, but it's quite difficult from the experimental point of view. All right, this was just a quick reminder. So again, here we have sharp conductive probe. This is so the vicinity of the conductive sample is about 10 power minus 10 milliamperes. This is the bias that I was talking about. And main limitation of STM is conductive sample. So if your sample is not conductive, then STM will not work. So what is here? So when we consider the separation between the tip and the surface as, let's say, as an ideal one-dimensional tunneling barrier, the tunneling probability, or in other words, the tunneling current I, will depend largely on K. K here is the distance between the tip and surface. And then if we try to calculate it, it will, so here M is the electron mass, E is electron charge, and W will consist of average work function of the tip and the sample and the bias voltage. So usually there is a very big equation here, but I just marked it as a working function. And H is the Planck constant. So how we can use all these values? So a simple calculation will show us how strongly the tunneling current is affected by the distance. So for example, if this K is increased by delta, let's say 1 angstrom, the current will change by 1 order of the magnitude, because we have E here and then the power. So that's the reason why we can get atom level image by measuring the tunneling current between the tip and the sample. So in a typical Stm operation process, the tip will be scanning across the sample in X and Y plane, and the instrument records the XY position of the tip. It will measure the tunneling current and also will control the height of the tip via the feedback circuit. So all the movements of the tip in X, Y, and Z directions are controlled by piezo ceramics, which will be like elongating or shortening according to the voltage that we're applying to them. Okay, so that was a bit of the just reminder what we had last time. So closer to the new stuff. So Stm scanning modes. Normally, there are 2 modes of operation for Stm. It is constant height mode and constant current mode. In constant height mode, the tip stays at the constant height when it scans through the sample. So here you can see if our sample is rough, then it will kind of mirror all the roughness of the sample, and the tunneling current is that we measure will be different depending on X and Y position. So this mode can be applied when the surface of the sample is very smooth. But if the sample is rough or has some large particles on the surface, the tip may contact the sample and can damage the surface. So in this case, the constant current mode is applied, which is shown here. And in this case, during the scanning process, the tunneling current will be stayed constant, but the distance between the tip and the sample will be variable. So, for example, if the tunneling current is higher than the target value, then this means that the height of the sample surface will be increasing, and the distance between the tip and the sample will decrease. So again, current is higher, height of the sample is higher, and the distance will be smaller. So in this situation, the feedback control system will respond quite quickly and retract to the tip. And then again, if the tunneling current drops below the target value, the feedback control will have tip closer to the surface. And according to the output signal from feedback control, the surface of the sample can be imaged. So again, this is constant current mode and constant height mode. So this is how it happens. So in Stm, bias voltage will be applied, and then a conductive and then the conductive tip and conductive sample we'll have this voltage between them. So when the sample is approached for a few angstroms from the tip, tunneling current will occur. So you can see the flow of the electrons, and this indicates the proximity of the tip to the sample with very, very, very high accuracy. So in a constant current mode, the operation of this operation, when we scan this the sample surface, the scanner keeps the current constant, and so you can see on this image that the vertical displacement of the scanner will occur. Okay, so and then here is the constant height mode. So here, Stm moves the tip only like in a plane, and the current between the tip and the surface will be visualizing the landscape. So this mode can be applied only if the sample surface is kind of flat. So, and all these differences, let me just laser pointer. So all these differences, although roughness here, they're not more than 5 to 10 angstroms. Otherwise, the tip will crash because we don't have the feedback loop depending on the height of the surface. And you should understand that the feedback loop will still try to maintain constant, like average tip to sample surface. We'll try, but again, the level, like it cannot change its height too much. So that's why I'm talking about the flat sample. Among Stm disadvantages, I can mention some of certain complexity of the result of the interpretation of the results of some surfaces. For example, for highly oriented graphite surfaces, I will show you this in the further slides. You can see only each second atom, not all atoms, and I will explain why. So that's why, even though it gives you very high resolution, it is not perfect in all cases. So talking about stop, please. Okay. So talking about resolution. So the spatial resolution is high, it's atomic scale. Individual atoms can routinely be measured, and you can even manipulate with these atoms. So this is the example of IBM research when they try to build this kind of a circular quantum well. So of course, to achieve atomic level resolution, Stm will operate in a very extreme conditions, such as ultra high vacuum, UHV, or cryogenic temperatures. You will need this to limit surface absorption of the different contaminants to the surface that can obviously influence the landscape. So the high spatial resolution, it can be achieved by quite harsh conditions. So I want to point out that STM is used in semiconductors fabrication a lot because due to this high resolution, it can spot the point defects in the lattice. So point defects, so you can see the lattice here is beautiful lattice here and here, but some of the places I'm showing you with my laser point is like some of the places I'm missing. So these are point defects, and these are lattice defects of zero dimensionality. So in other words, they do not show the proper lattice structure of any dimension. So what kind of point, what is it like in real life? Typical point defects are impurity atoms in a pure metal, or it can be vacancies or self interstitials. So why we need to know this information? Because we need to control these point defects in semiconductors. If semiconductor does not have any defects, then it is not a semiconductor. And it is very important for like fabrication process to control the concentration of these defects. Yeah, that's why STM is used in this process. And these defects can occur in general for like three main reasons. So first of all, of course, it is impossible to obtain any substance in 100% pure form. Some impurities will be always present. And even, let's say, we just imagine in an ideal world, even if a substance is 100% pure, forming a perfect crystal will require big cooling of the liquid phase and infinitely slowly, and so this will allow all atoms, ions, or molecules to find their proper positions. So we cannot cool down the sample that slowly. So cooling at more realistic rates usually results in one or more components being trapped into the wrong place in the lattice, or in areas where, let's say, two lattices that grew separately like intersect. And the third reason is that when we apply an external stress to a crystal, it can cause microscopic regions of the lattice to move in comparison with other regions, and this is resulting to like not a perfect alignment. And here I will talk about graphite a bit. So HOPG is a highly oriented pyrolytic graphite. So this is the material that is characterized by the highest degree of three-dimensional ordering. So I hope you remember from your chemistry classes in the school about like the graphite. So this is not usual graphite, it's very highly oriented one. And it's usually used as a substrate for your samples. And in particular, like mica, HOPG belongs to lamellar materials because of its crystal structure. It's characterized by an arrangement of carbon atoms that are stacked in parallel layers. So carbon atoms within a single plane will interact much stronger than those from the adjacent planes. So this is plane 1 and this is plane 2. So that explains the characteristics of cleaving behavior of graphite and mica as well. So in your practical sessions, you will learn how to make your substrate before you put your sample on very flat. So that's called cleaving. And because the graphene here is planar and has hexagonal arrangement of carbon atoms. So the usual typical lattice of graphene consists of two equivalent triangle carbon sublattices. So A and B, A is marked in red here, B is marked in blue. And they're just alternating. I will explain further why here is like it's blue and red, not the one color. This material as a layer is an excellent tool to use scanning probe microscopy. Stm and Afm as a substrate, as I already mentioned. And but there are some experiments assessing how flat it is, and then let's say we have a question: can we image it with the atomic resolution with Stm, for example, right? So in atomic resolution of if we use SPM, we can get two possible images, as in the red color A atoms, or only in the only B atoms in the blue color. So the distance between these imaged atoms is about 2.5 angstroms. And if we talk about 6 hexagonal atom, distance between two atoms is 1.4 angstroms. So the atomic pattern that is normally observed in most SPM images is like bright spots that originate from only 3 of carbon atoms out of set of 6 in the honeycomb. And each apparent atom is surrounded by 6 nearest neighbors. So the distance between any of 2 of these atoms that are that we can see in SPM image is about 2.5 angstrom, as is depicted here. And this is commonly reported for all HOPG surfaces. And the characteristics features of SPM images are interpreted in terms of AB stacking in graphite. So the asymmetry in the surface atom environment results in a threefold symmetry, or so-called 3 of 6 pattern. So let me just show you the actual images. And okay, so before that, we were talking with you about constant current mode and constant height mode, and I want to use HOPG as a substrate and then show how it looks differently in different modes. So that's why we need 2 modes, not 1. So here we will, I will talk a bit about constant current mode. So this is the reported experimental STM image with atomic resolution. So here you can see this triangular structure from all this lattice size. That's what I was talking about in the previous slide. And again, this image is obtained in a constant current mode. So the tunneling current here is about 0.4 nanoamperes, and the voltage is about minus 50 millivolts. So on the image that is B here, the blue dots, it shows the calculated STM image of the constant height mode with the same bias voltage. So you can also predict how your images will look like if you use density functional theory for like atomic resolution. You cannot predict all images, of course. So this is the predicted image, and this is the real image that researchers saw. Here on C and D, you can see profiles, and there here we can see the length on the x-axis, and the y-axis is a height. So each bump here corresponds to 1 atom that was detected, and here is the distance between the atoms. So, but make sure here the length is depicted as nanometers. What I was talking here is angstroms, so 10 times less. So this means that here's 0.25 nanometers, and is what you can see here, 0.25 nanometers between each atom. For the comparison, here is a TEM image. This is transmission electron microscope image, and it shows the actual lattice with hexagonal structure. So again, so here, so among all the 6 carbons in the ring, only 3 atoms can be imaged under constant current mode, because these 3 carbons give much higher tunneling current, because they have a bit higher local density and state, and this effect is called giant corrigations, or enormous apparent height of atoms. So this is just the local differences between these atoms in comparison with others. So this is the constant current mode, and let's go to a constant height mode. So this is the calculated image again, like what we should see like in the ideal case situation. And please look here. So even though in the constant height mode we can see the honeycomb structure, so kind of hexagonal one, 3 atoms out of 6 are still much brighter than other 3. Can you see this? So this image was taken under tunnel current range that goes from 0.1 to almost 2 nanoamperes, and the voltage was much lower than in constant current mode. It was minus 300 millivolts. It's much more negative, sorry. So the experimental image and the calculated image show that the even like in the calculated one, 3 atoms are more bright, they're brighter than other 3 atoms. So both of these images, they show us that the current maximum of 3 of the 6 carbon atoms. And so from the calculated image, it can be identified that the carbon atoms of each lattice side can be seen actually, right? But the brightness is very different. So what kind of conclusion we can get from all of this? So in general, measurements in the constant height mode are they can give you a bit better resolution, but they're much more difficult to be performed in comparison with those in a constant current mode. Why? Because the feedback control here is much more difficult. But this constant height mode is very different, and they're very important in order to achieve this full hexagonal graphite structure. So, for example, if you have a very, very flat structure that you need to image, then it probably is better to go to constant height mode rather than constant current mode. Okay. So this was the difference between constant current, constant height mode. If you have any questions, I can answer them now. If you don't have any questions, we will proceed to examples of different images that we can get by STM. So first image in the top is a single-walled carbon nanotube. And this is the 7 nanometer long part of this nanotube. So they are quite interesting material to image because they can exhibit either metallic or semiconducting behavior, depending only on its diameter and helicity. So that's why you need STM to characterize them, because you need these parameters, diameter and helicity. So these carbon nanotubes can be so. For those of you who doesn't know what is this, so these are the extended fullerene molecule cluster, and major characteristics of the electronic properties of carbon nanotubes can be built from Huckel type models using p atomic orbitals. So a single-walled carbon nanotube is an allotrope of sp2 hybridized carbon, similar to fullerenes. And the structure can be thought of as like a cylindrical tube that is made of these hexagonal carbon rings, as in the graphite that we just literally saw right now. These cylindrical tubes have one or both ends capped with a hemisphere of like the buckyball or fullerene structure. So what kind of properties we can assess with STM? First, the mechanical properties. So because usually individual nanotubes, they are significantly stronger than the steel. So for example, calculated values for tensile strengths of nanotubes are about 100 times greater than steel in the 1/16th of the weight. Obviously, the production of the steel is much cheaper. That's why we still use steel, not carbon nanotubes. In terms of like electrical properties, individual nanotubes have current carrying capacities of about 100 amperes per centimeter square. This is higher than in copper and gold, and semiconducting species exhibit higher electron mobility than silicon. So again, that's why I use STM to characterize them, because they have semiconducting properties. So this is just short explanation about carbon nanotubes. So the next picture is silicon carbide that again supposed to be packed in a hexagonal lattice, even though you see like what you see is mostly like triangles here. So silicon carbide is a semiconductor material, and power devices based on silicon carbide, not just silicon, or they usually offer like various benefits over conventional silicon devices. For example, they have high voltage and high frequency capabilities, and they allow greater system efficiency and faster switching. What else? Lower losses. They have better thermal management. And also these kind of devices that allow small and high power designs and fit like because of the high power density. So that's why it's one of these new materials that are being investigated recently. And in the bottom, you can see unfolded bovine serum albumin, BSA, that is just lying down on the surface. And investigation of proteins with STM is quite a recent approach. And here, each dot represents one amino acid. So you can check the protein with single amino acid resolution. So this part is about 80 nanometers, the big one. So this is the part of the whole molecule here. Yeah, so the resolution of the structural details is amazing, and unfortunately, currently it is not possible to identify the amino acids like chemically, because even though each spot represents amino acid, we still, even here, we don't have the atomic resolution to understand what amino acid is where. But we are able to observe and manipulate proteins as a polymer. So, for example, here, unfolded protein is visible as a meandering strand, and especially when they immobilized on the surface. And depending on the charge of the protein, the proteins can adopt straight or more compact conformation. And some of the proteins, they have several charge states, so they will have different conformation for each charge state. And if the unfolded proteins are given the freedom to diffuse, for example, you can depose them on a weakly interacting surface like gold, they can fold back into 2 dimensions in a very compact low energy conformation. So there are like a full bunch of experiments are going on in this field. And some people even try to do folding in a vacuum, but again, it's quite difficult to perform. And so this kind of approach is usually referred in the literature as a single molecule force spectroscopy, and it's quite a powerful tool to study protein folding. But one of the key questions for all these kind of studies, all these changes of the biomolecular dynamics, is it influenced by attachment forces or linkers? Because usually if you want to study the folding of the protein, you usually attach it by one of the ends, either C-terminal domain or N-terminal domain, to the surface. So you should remember, like, don't forget about how long is the linker, can it influence on the protein folding or not, because if it's too short, then the folding can be affected by the surface to what the protein was attached to. Okay, so I think this is the end of the story for scanning tunneling microscopy, and we are going to AFM. So AFM was developed to overcome the basic drawback with Stm. Stm, again, can only image conducting or semiconducting surfaces. So the AFM has advantage of imaging almost any type of surface, including polymers, ceramics, I don't know, composites, glass, or biological samples. And one of the main forces that is used here is like dipole-dipole force, van der Waals force, exchange forces, all these forces that we were talking about last time. So we use needle or tip to measure the displacement of the cantilever. Oops, sorry. And traditionally, most AFM use a laser beam that forms a deflection system where the laser is reflected from the back of the cantilever and then is being detected by a position-sensitive detector. So, and regarding the material of the tips and cantilevers, they are typically microfabricated from silicon or silicon nitride, depending on the application. And typical tip radius is about from several nanometers to like 1/10 of a nanometer, depending how sharp tip do you need. Okay, so now a bit more about the detection. So there are a number of ways to detect the deflection of the cantilever in an IFM. So the most common method, again, is the using of a laser beam. So we have a diode laser that is focused on the back of the reflective surface of cantilever and then reflects back to the photodetector. So depending on how the tip is bending, the position of these spots goes between. So usually there are 4 quadrants, is 1, 2, 3, 4, and it will detect the bending in different directions. So this is the vertical bending, so goes between quadrant 1, 2, and 3, 4. And in case of the lateral forces, when the cantilever bends in a lateral way, it will be, this spot will be traveling between quadrant 1, 4, and 2, 3. So again, so this detector is called position sensitive photodetector, or PSPD. And the position of this beam is quite often used in lateral force microscopy when we're trying to measure the adhesion forces and lateral forces in a sample. So we choose special type of the cantilever that bends a lot in the lateral way. These are that I was talking about, the vertical deflection and lateral deflection. And this is the video on basically how AFM works as a scanning microscope. So you have an optical system that goes on your substrate, and then you have the profile being recorded. Okay, okay. So depending on the mode of the AFM, so it can be tapping mode as is shown here. So basically the tip taps on the surface. And then you can receive the graphs about force depending on the height between the tip of the cantilever and the sample. Oh, all right. Let's go back to the deflection. This is vertical deflection and lateral deflection that I was talking about. And these are the current, intensity of the signal in different parts. So originally there were only 2 parts, but nowadays we usually use a quadrant photodetector. And so the center of entire detector here, this center outputs 0 volts. But as the laser spot moves to like different radial distance from this center point, the magnitude of the voltage in output will increase in a linear way. So here X and Y. X is a horizontal movement, Y is vertical movement. So vertical deflection can be defined as this combination of the intensities. So A, B, C, D is the intensity of each quadrant. And then it's normalized by the sum of all intensity from all quadrants. So these are the formulas for these, for vertical and horizontal, lateral deflection. So for the quantitative imaging, we really need these approach of these quadrants, the fluctuation of the laser beam is will be used as for further calculations. So the question that we have raised is how to keep the distance. We used a proportional integral derivative controller, or PID. So its parameters play, I would say, a vital role in the imaging process of an AFM. So traditional parameter tuning methods require like a lot of manpower, and it's difficult to set these PID parameters in unattended working environments. So that's why this control is one of the core components of AFM. And it is used to maintain an appropriate distance between the sample and the probe. Okay, so what we can see here. So first of all, I would like to introduce you some terminology. So what we are looking at is a set point. Set point is the value that we want the process to be. So for example, this controller will look at this set point and compare it with an actual value that we are having from the process. So the actual value is called process variable. So if set point and process variable are the same, then the controller is happy and doesn't do anything, and it will set its output to 0. But if there is any discrepancy between set point and process variable, then we will have an error, and then this controller will try to correct this error. Let's define all this RT, ET, UT, and YT. What is that? PID controller will continuously calculate the error value. Error value is shown here as ET. So the difference between our set point and process variable. So the difference will be the YT. So this is what was calculated by our controller. So basically it is the difference between the set point R minus this error. And then the corrections will be based on 3 terms: proportional, integral, and derivative corrections. So let me just explain you each one what they do. So let's talk with the derivative. So the derivative is just a mathematical term of a rate of change. So for example, how quickly we will respond. Integral gain is, if you remember, I hope you remember from the school and from the university, that integral is basically the area under the curve. So when we have real-world system, we have to approximate this area under this curve. So more sampling we're doing, better approximation is. So this is the integral gain. How often we are taking the readings. And the proportional gain is basically, if we use only this term, then the controller will multiply error by proportional gain to get the output. So the good PID will calculate all of these terms, specifically integral gain, to apply for all the processes. And for example, let's just go by one by one. How to adjust integral action? So the question is how often we need to get the readings, right? Basically, the controllers have an alternative unit, the repeats per unit, and then that's how it gets the fast response. And the proportional gain is basically, if the error is quite big and positive, then control output will be proportionally large and positive. And then the controller will adjust the system until this difference will be as small as possible. So let me just go in a bit different way, the explanation. So how this PID works. So here, these adjustments in the mathematical terms, they're called Ziegler-Nichols tuning method. It's a heuristic method for tuning the controller. So it attempts to produce good values for all three PID gain parameters. So Kp here is the controller path gain, Ki is the integrator time constant, and Kd is derivative time constant. What we are doing here is we try to change each parameter one by one, and then try to gain as low oscillations as possible in the as a final result. So, for example, we set Ki and Kd to 0, and then we start with Kp value, and then once we gradually increase, just a moment, we'll start. Ki will gradually increase, and then we will have more oscillations here happening. Once this one is happening, then we start to tune the next parameter to reduce all these oscillations. And the thing is that to try to reduce the overshoot thing. So, for example, this one is the overshoot, and that's when the system is not optimized correctly. Okay, so let's talk about PID in actual images. So talking about AFM, depending on the different modes in AFM, we have different set points. So for example, in a contact mode, the feedback parameter in cantilever is deflection of the while in the tapping mode, the feedback parameter is the oscillation amplitude of it. So the instrument is trying to keep this feedback parameter constant, and its set point value by adjusting to these piezo actuators using voltage. So control of feedback loop is done through the proportion for these PID gains that we discussed before. So these different gains, they will refer to difference in how the feedback loop will adjust the deviations of the set point value. So for AFM operation, the integral gain is the most important and has the most dramatic effect on the image quality. The proportional gain can provide slight improvement after optimization of integral gain. And then derivative gain is mainly for samples with very tall edges. If gains are set too low, these PID controller will not be available to keep the set point accurately. And if the gains are chosen too high, the result will be the electrical noise of the image and from the interference from the feedback loop. And then the compensation of this deviation from the set point will be larger than the error itself. So the noise will basically spoil your image. So here, for example, all the noise, the gains are very high. Some noise that you can see still as these sharp horizontal lines, you can see your sample, but the noise is still kind of high. So this means gains are still too high. And these are the best settings here in the green. So you don't have any parallel or any sort of like lines. You have your own sample here. And then if the gains are too low, then the tracking is very bad. So these gains can be adjusted in the software while you're doing AFM measurements. For other parameters that about other parameters that are important for feedback control, it is also scan rate. If your scan rate is too fast, then PID loop will not have sufficient time to adjust the feedback parameters to its set point value. And the height will be calculated from the zero piezo movement, and they will deviate a lot depending on the slopes and edges in your sample. If you have very slow scan rate, it is typically not an issue about that you will be sitting in front of the microscope for ages. So it's no issue for PID loop, but yeah, long acquisition times. And also what can influence is a thermal drift. We will talk about all these artifacts later, but basically if the temperature in the room is too high, then these effect will occur, and it will result in a very blurred image. So optimization of PID gains and the scan rate are necessary to optimize feedback loops and get the better images. So the set point itself affects the interaction force or impulse between probe and sample, and a set point close to the parameter value, like outside the contact feedback, is the most gentle of this, is the most gentle for the sample itself, but it kind of slows down the feedback control. Do you have any questions about the gains? If not, then I would like to go for operation modes. So all this contact mode, not contact, and tapping modes that I was mentioning before. So let's just have a small overview of them. So AFM has three, basically all the AFM modes can be divided in three groups: contact mode, tapping, and non-contact mode. So I will go with the contact mode first. So LG here is the Lennard-Jones potential. So contact mode, it was basically the first mode that was developed for AFM. And it's kind of simplest. So you just drag your tip along the sample surface here. There are some limitations of the contact mode. That's why non-contact and tapping one were developed. But the good thing is that it is the fastest of all topographic modes, and because the deflection of the cantilever directly shows the topography of the sample, and there is no summing of the oscillation measurements here that are required, and so on. What kind of implications of the contact mode AFM exist? So as a result of the repulsive force between the tip and the sample may be damaged or changed by the scanning process, because your tip constantly is touching your sample. In other way, the tip can also be damaged or changed by the scanning process. So it's cool. So you should choose the mode depending on the type of your tip and your sample, and vice versa. So so tip and the sample are constantly in contact with each other. So to addition to the normal force that they apply to each other, lateral forces are experienced by both the tip and the sample. Yes, so in the contact mode, the force is calculated using Hooke's law, and the feedback circle adjusts the probe height to try to maintain a constant force and deflection of the cantilever. So this is known as a deflection set point. Okay, so what are the advantages? Advantages is a high scan speed, this is one of the few AFM techniques that can allow us atomic resolution images, and some rough samples with very, very big changes in the vertical topography sometimes are easier to scan using contact mode. Again, the disadvantages are lateral forces, and combination of the lateral forces and high normal forces can result into reduced resolution due to damage of the tip or the sample. Okay, next is non-contact mode. So both non-contact and tapping mode, they use oscillations here. So the tip is just vibrating basically. So one of the great advantages of these type of modes is that they decrease the size of tip to sample forces, and at the same time they maintain very high sensitivity to the sample topography. How we can achieve that? The tip must be close enough to the sample surface to achieve high sensitivity, and the oscillation is slightly above the resonant frequency. So the van der Waals and other long-range forces decrease the resonant frequency just above the surface. And this decrease in resonant frequency causes the amplitude of the oscillation to decrease as well. So a non-contact mode, the best performance of it usually in ultra-high vacuum conditions. So the the cantilever here should be quite stiff, and its resonant frequency is about from 100 to 400 kilohertz, and the amplitude is from like 10 to 100 of angstrom. Okay, so typically non-contact mode is carried out in the amplitude modulation mode, and the error can come from either from the amplitude or the phase of oscillation of the tip. So to avoid the different possibility of like sleeping or drifting, it's very important, because otherwise you can damage or contaminate the tip. Okay, and then next is a tapping mode, is one of the most popular modes. So tapping mode, it oscillates on a slightly below its resonant frequency. Just to remind you, in non-contact mode, we oscillate slightly above the resonant frequency. Here, we oscillate slightly below. So the amplitude of oscillation typically ranges from 20 to 100 nanometers, and tip slightly taps on the sample surface. So it's touching, but not constantly like in contact mode. And because the forces on the tip change as the tip surface separation changes, right? It touches and then removes, touches, removes. So because these forces are changing, the resonant frequency of the cantilever is dependent on its separation. And oscillation is also damped when the tip is closer to the surface. So the feedback circuit adjusts the probe height again to try to maintain constant amplitude of oscillation. And here we have amplitude set point. Just to remind you, in contact mode, we had deflection set point. Here is the amplitude set point. And the cantilever oscillation amplitude will change with the sample surface topography. Yes, and then tapping mode was firstly developed by the company called Bruker, and it's one of the most popular modes. What are the advantages of the tapping mode? Is very high lateral resolution on most of the samples from 1 to 5 nanometers. It has lower forces and less damage to soft samples, especially if you do the acquisition in the air. And again, the lateral forces are almost eliminated because there is no scrapping as in the contact mode. So it gets all the best features from both contact and non-contact modes. And then disadvantages is a bit slower scan speed than a contact mode AFM because you're not going, let's say, from the left to the right, you're also going up and down. That's why it's slower. Okay, and here the examples of Afm operation. So this is how the profiles usually look like, especially when you have step height measurements. And here I want to talk about the hybrid mode. So before that, we were talking about contact mode and basically oscillation modes with some sort of the resonance, right? But hybrid mode is oscillatory non-resonant mode when probe and the sample are brought into intermittent contact with vertical direction, and the probe in deflection is also induced, and we use it for tracking feedback. The basic idea is to minimize the lateral force and interactions between probe and the sample. So in this mode, the sample and the probe, they interact at a frequency below the resonant frequencies, and the probe deflection level is more directly related to the tip surface, tip sample forces, because here we also check the deflection, but because of the vertical movement, it sometimes is not the linear correlation. And these allow us to get different information out of the sample. So this is PDS layer on silicon, and it allows us to get the height, also the adhesion and the stiffness of the sample. So strong adhesion can be observed here, and this mode helps distinguish different variations in adhesion and stiffness like independently. And yes, it's quite useful mode, and some of the AFM machines have it. Okay, and then we have a bit time left to talk about force distance curves. So first of all, I just want to define some terminology. So what is force distance curve? So in AFM, we can study features of the local force interaction that gives us information of the sample surface properties, right? So with this purpose, we have force distance curves. So when tip is approaching to the surface and when it's retracting from the surface, and when we measure it, then we get this kind of information. So force distance curve plays like quite an important role in explanation of different types of interactions and physics behind the interaction. So what we measure in AFM is the distance between the cantilever and the sample. Please be careful. Cantilever is the whole thing here. So the cantilever and the sample. This is Z in this picture. And this is not the distance between sample and the tip. Tip is this thing here, and the distance will be D. So please do not mix cantilever and the tip. So the distance controlled during the measurement is not the actual tip sample distance, but the Z distance between sample surface and the rest position of the cantilever. Rest position is like when it's not touching the sample. And these two distances, D and Z, they differ because of the cantilever deflection. This is here is called as delta C, the deflection, how it moves, and the sample deformation, delta S. So here it can be volume is going down or up depending on the sample. And it all reflects this kind of equation. What we get as a force distance curve is a force versus z distance, not force versus d distance and the graph. So how they look like, these curves, they look like this, basically. And during approach to the surface, so here blue is approaching, red is retracting from the surface. So during approach to the surface, tip gets in the reach of attractive forces, and this causes a cantilever to bend towards the surface. So when we have a further approach of the cantilever to the sample, then tip starts to experience repulsive force, and then it bends in the opposite direction. So the slope of the curve is basically delta z here, is the region which is determined by elastic properties of the cantilever and the sample. And if the interaction is perfectly elastic, then dependence of the band of the distance is recorded during this reverse motion. And so this is like the theoretical curve. This is how they look in actual experiments, I would say. And so we can obtain different mechanical properties of the sample surface, checking the first separation curves. For example, the stiffness of the sample can be determined from the slope and force separation curve. And then we can check the Young's modulus. We can also determine the geometry of the tip sample contact, and so on, and then calculate different models. And here, I would just want to show you the examples of different shapes depending on the sample and the force and deformation. So again, this shape is strongly depends on the tip sample and tip sample interaction, right? So so when we compare the contact region of these curve for hard and soft sample, it becomes clear that the slope, so hard samples and soft samples, right? So it's quite clear that the slope of the curve increases, right? Increases with increasing the hardness of the sample. Accordingly, like a cantilever is strongly deflected from the hard samples at the same height, because hard samples cannot be indented as easily as soft samples. If we talk about adhesive forces, so adhesive samples require higher restoring force to separate the tip and sample in comparing with low adhesive samples. And this reflects in a larger amplitude in negative direction here. You see this difference. So, and depending on the properties of the cantilever and sample, tip can cause elastic or so means reversible or plastic or irreversible deformation of the sample. So here you have elastic and plastic deformations. So anyways, if the sample is compressed excessively by hard cantilever, the sample surface will deform irreversibly. So that's why it is important to understand the properties of your tip and the cantilever. All right. And the last thing that I want to talk about is functionalization, specific probe sample interaction. And these interaction can be mediated by modification of the tip, or we can also modify the sample, and we can detect different surface properties like if they are conductive or dielectric, if they, let's say, hydrophobic or hydrophilic, and so on. So what kind of tools can be provided by AFM? So this is like a scanning probe technique, right? So it gives us quite unique possibilities for characterization of cells and cell machineries. So here we can use AFM probe to contour. So here, So here there is a dashed line. So this line is contouring basically a topography of biological membranes, and we can do this under physiological conditions. And the resolution can be sufficiently high and show us separate membrane and individual membrane proteins. And all the applications that can be then AFM can be used for listed here. So for example, we can develop characterization of biological objects using functionalized probes. They're shown here in the bottom. So we can have some polymers attached to the tip. We can have conductive tip. We have charged tip, and so on. We can have cells or viruses as objects for investigation of the membrane proteins. Different strategies that can be used for tip functionalization. How this process works. So first, you have to choose an appropriate AFM probe. So usually the most important consideration is the spring constant of the cantilever. But sometimes, depending on your application, its sharpness can be also important. And molecular binding interactions are usually quite small, so you might want to use soft cantilevers with a spring constant less than 0.9 newtons per meter. If the interaction should be used quantitatively, so the spring constant must be calibrated as well. Second point is that you also should think about the functionalization chemistry for your tip. And you should keep in mind that the ligand molecule must be attached to the tip in a way that the binding strength between this molecule and the tip is greater than the interaction between ligand and the surface receptor. So what I'm talking about, if you have something on the tip attached, this attachment should be stronger than the interaction between the tip with this functionalization probe and the surface. And then next thing is that in the cases where we want to catch a single binding event, we should also think about the limit of the surface density of the ligand and on the tip. Very often we might want to use the different linkers. The example of these linkers are shown on these slides. And for example, we use a protein, so the linker can use a his tag. It's usually about 6 to 10 histidine amino acids attached to the tip. And it gives certain level of freedom to our modification probe, and because it has some distance from the tip. And the functionalization itself is almost always a multi-step process, but like fundamentally, it is always starts with a silicon or silicon nitride. So this silicon or different silicon nitride, modifications. And after that, we very often add amino groups, and then to these amino groups we can add different carbons and then proteins. So this is like a multi-layering approach when you can attach something to the surface of the tip. It's just example of different nanomechanical properties as and what we can do this. So here's like the steric zipper of the globular structures. So here you can see the representative force to distance curves measured between this hexapeptide on Afm tip and the globular structures on the surface. So this is the schematics of how it looks like. And at the panel B, you can see a representative force curves. So, for example, curves from 1 to 3, they show us non-specific interactions between Afm tip and the surface. Curve 4 shows us the overall behavior of the modification. And curves 5 and 6 will show us the basic nanomechanical fingerprint of the hexapeptide globular structures. So if you remember the details about the curves, you can see that depending on what area we're focusing on, we can get a bit different curve, and we can characterize the behavior of the sample checking these curves. So I think this is all for today.
С вами был Тибериус. Если видео понравилось, ставьте лайк. Если видео не понравилось, так уж и быть, ставьте дизлайк. Но обязательно напишите почему. Подписывайтесь на канал. Всем пока. До скорого.